Hey there, math enthusiasts. I had some spare time and I wanted to make a video proving the Pythagorean theorem so that if you're interested in math and maybe want to pursue it later on in life, you might see the sort of stuff that you would be getting into, because in college, it's all about proving things. So like the Pythagorean theorem, everybody knows that the Pythagorean theorem is a squared plus b squared equals c squared. Remember, the a and the b are the legs, these guys, next to the right angle. And the c squared is the hypotenuse, and there's this incredible relationship that a squared plus b squared equals c squared. But the question is, why is that the case? And I should be able to prove that somehow. Why is it not 2a plus 2b equals 2c? Why is it not a times b equals c? I don't know. So as I was thinking about this problem, I didn't know how to get it from just a triangle. I need some more triangles, so I decided to do this, and this is where proving things in math gets really fun, because sometimes you don't know what you're supposed to do, and you can try something. And the thing I came up with is this. What if I can arrange a couple of copies of this triangle into a bigger shape of some kind? So here's what I'm going to do. I'm going to copy this triangle, and I'm actually going to paste it a couple of different times, and I'm going to see if I can rearrange a couple of copies of this triangle into a bigger shape. And here's what I came up with. I want to arrange these triangles into a really big square. So I'm going to rotate them, and I'm going to put them together in such a way that they make a square. So again, what I'm doing is I'm just taking the copies of this triangle and I'm rearranging them into a square. And you'll see what it looks like in 1 second. Whoa. So, look what I did. I just made a big square. Do you see it? If you don't, kind of tilt your head sideways. I just made a big square out of a bunch of this right triangle. So now that I have a big square, I might be able to find some relationships based on different ways of calculating the areas. So just a real quick reminder of what's going on here, and now that I can write on my screen, I know that the A we're going to call the short side, and the B is the long side, and the C we'll call the hypotenuse. That's normally how these right triangles are set up. A and B don't necessarily have to be short and long. That's just how I decided. So in each of these copies, let's label the sides. This one is going to be A, this one B, this one C. A is short, B is long, C is hypotenuse. A short, B long, C is hypotenuse. Okay, now if you notice, if you look at this big kind of diagonally oriented object, I have a square. I know it's a square because each side is C, and I also know it's a square because I actually have right angles in this corner. Now, a question you might be asking is, how do I know for sure that these are right angles? I'll just talk about this briefly. Basically, I know that all of the angles in a right triangle or any triangle add up to 180 degrees, right? But a right triangle is unique because since I already have a right triangle, I know that this angle and this angle are actually going to add up to 90 degrees because the other 90 degrees to get me to 180 is taken up by the right angle. So isn't it true? I'll say this. This little dot, and I'll call this a little star, they add up to 90 degrees, right? Because the angles overall have to add up to 180. But isn't it true that this star is the exact same thing as this angle, right? Because all these triangles are just copies of each other. So in other words, I'm saying, hey, these two angles, they add up to 90 degrees, which proves that what angle do I actually have here? When I put the two together, a right angle, a 90-degree angle. So yes, this big figure is a square. It has all right angles. All of its sides are C. And so the area of the square is C squared because that's the area of a square. I take this side times this side. C times C is C squared. So the area of the big square that I'm going to shade in right now, the area of this whole thing is C squared. But wait, I made this big square out of a bunch of little triangles, right? So I should be able to calculate the area in a different way. So here's the first way of calculating the area. I should be able to calculate the area in a second way, right? And the way I'm going to calculate it a second time is, instead of looking at it all as one square, I'm going to look at it as the 4 separate triangles and then this mini square inside. If I add up these 4 separate triangles and the square on the inside, isn't that true that it's giving me the area of the whole big square? But I'm doing it in a different way. I'm doing it by adding up the 4 triangles and the square on the inside. So it's really easy to find the area of each triangle, because remember, the area of a triangle is 1/2 base times height. Here's the base, we'll call it b. Here's the height. So the area of one of these triangles is 1/2 AB, but how many triangles do I have? 1, 2, 3, 4. So I actually need to multiply this by 4 because there are 4 triangles. Okay. Now, if I can just find the area of this thing on the inside, then I should have the whole area of the figure, right? I've already taken care of the triangles. If I can just find this area, I can add them together, and I'll have the area of the square. What are the side lengths here, though? Well, I know that from here to here is B, right? And I know that from here to here is A. So if the whole way from here to here is B, and then the whole way from here to here is A, isn't it true that to find just this length, I need to go B minus A, right? Because if I add up these two things, B minus A plus A, it's going to get me the whole length of B. And that is also true because these are all copies of the same triangle. That's also going to be true of this side length, which means that in order to calculate the area of this square, again, I'm going to do the side squared. In other words, the area of this square is B minus A squared. So in order to get the area of the whole big thing, I take the 4 triangles, their areas, and I'm going to add to it the area of that little inside thing, B minus A squared. Interesting. So I actually have 2 different expressions that perfectly express the area of the big square, but in different ways. So since I'm expressing the area of the big square in different ways, I can set them equal to each other. It's the same area, right? I just wrote it in different ways. So I can go 4 times 1/2 AB plus A minus B squared. That's this area. And I can set it equal to C squared because they both are the area of the figure, but in different ways. Now, we need to simplify some things because there is some stuff that can be simplified. For example, 4 times 1/2 is 2. This, since it's A minus B squared, is A minus B times A minus B. And this looks an awful lot like a FOIL problem, right? So let's FOIL this. A times A is A squared. A times negative B is negative AB. Negative B times A. I'll write it as negative AB, right? I can do multiplication in any order. Negative B times negative B is positive B squared. And I'll just rewrite all my other stuff. Okay, let's start combining like terms here. I have 2AB minus 1AB minus another AB. Oh, so doesn't that mean there's 0 ABs? In other words, these things cancel because they're like terms, and 2 minus 1 is 0. So these guys actually cancel. What am I left with? A squared plus B squared equals C squared. Whoa, I just proved the Pythagorean theorem by making a big super shape out of triangles and calculating the areas in multiple different ways. That's crazy. And because I've proved it, I can write this little square afterward, which means it's proved. This is the sort of thing you do in college, and how fun was that? I at least enjoyed myself, and I hope you did too. Have a nice evening.